next speaker is Will Brackenbury from Denison University, and he will be discussing K-regret queries with nonlinear utilities.
Hi everyone, my name is Will Brackenbury, and with my research partner Taylor Kester, there she is, she was hidden from me, Taylor Kester Faulkner, and my research advisor Dr. Ashwin Lal in the Department of Mathematics and Computer Science, we've been working on representative databases this summer. So our basic problem is as follows. Let's assume we have a large database, and by large this can mean anywhere from 100 to 1,000,000 items. And in this case, for our example, let's assume it's a database of cars. And to further simplify the problem, let's assume they only have two attributes that we care about, which would be horsepower and miles per gallon. I'm sorry if you like the color. So the basic idea with this problem is that for a sufficiently large database, then any user who tries to look through it to find their car, their favorite car in the entire database, has to search through a lot if they want to get their perfect point. And so our goal with representative databases is to narrow this down into a more manageable region that they can look at, say 10 items. So the first approach to doing this kind of work that's been looked at in the past is known as the skyline query. And the basic idea of it is that, as you can see, there are a couple points on the interior of this hole that they're points no one likes. Basically, they're points that they're going to be worse than another type of car in the database in every single way. And so what this means is we refer to them as being dominated. So in this case, the point up here in red, like so, is one point that dominates this point over here. So it gets removed from the database. And in this manner, we can remove a lot of different points like this, and that narrows down our selection size. The problem is, this doesn't actually narrow it down a whole lot. There can still be a lot of different cars in the database, especially when we start choosing more and more attributes, like if we look at safety rating, then one of those points in the interior might in fact have a better safety rating, and so the user has to look through that one too, even if it's not that good. Another problem is, if you're making cars that are on the interior of the hole that are worse than other cars in every way, you're not going to be in business long. So it kind of eliminates those as a matter of fact. The other approach that's been looked at before is top K query. And it gets its name because it returns the top K number of results for any user. As I was talking about earlier, usually it's 10 results roughly. But in top K, they assume that every user has a utility function. They have certain preferences, and they do have a car they can pick up based on those preferences. So if we have points A, B, and C, for example, then a user might have a utility function where they have a weight of 0.75 for the horsepower, but they care about miles per gallon a little less. They have a weight of 0.25, let's say. And so point A, for example, would have a utility of 3. These units aren't completely correct. You are going to have 1 horsepower, I hope. But this would be the utility for A. Point B is a little closer to what they want because it's a little more horsepower. Did I mix those up? I don't know. So it would have the utility of 4. And point C, that's going to be their favorite point. That's going to be ranked the first because it has a utility of 6.25. The difficulty, of course, with this is I don't have a mathematical model of my preferences. I don't even know what I'm looking for a lot of times when I go to a website. So that's one difficulty. Another difficulty is even if you do have kind of an idea, then you might be lazy and just not want to put them in because you still have to tell the computer what you want. And I know I'm lazy. That's too difficult for me. So this is still prior work, but the approach that we built upon this summer is called the K-regret query. And so it uses the same K as top K because it returns 10 different items, but we don't need to know the user's utility functions. It works like this. Let's say we return to the user the points in red, A, B, and C, and their absolute favorite point in the database was point P star up there that's highlighted in green. Use the laser pointer. It's the point in green. Essentially, we're not going to show that point to them, but point A actually is going to have a pretty similar utility function to point P star. And so we say that the user's regret, or their regret ratio is the metric that we like using, is the utility that they would have gotten from P star versus the utility they get from A all over the utility they get from P star. It's basically a metric saying how close did we get with the points that we returned to the user? How satisfied are they going to be? So the problem is a little more complicated than that, unfortunately, because a lot of times, here's our example of the utility function we might use again. But a lot of times the problem can be more complicated because, again, we don't know the user's utility functions, so we don't really know what their ideal point is going to be in the database. It could be any of those guys there. And so what we have to do is we don't have to just make one user's regret ratio as low as possible. We have to return a set of points so that for every user, you're going to have a particular regret ratio that's the worst possible. We want to see how bad we do for the worst possible user. So the maximum regret ratio is something that looks a little bit more like this. From any point in the database, the user's ideal point that we return to them, then how close do we get to their favorite point for any given user. So this is the basic idea of the K-regret query. But so far, I've only shown you guys linear utility functions. And the difficulty is this doesn't always model users' preferences. So our work that we did this summer was focused on expanding this model to nonlinear utility functions. Now, the line A, for example, is simple weighted preferences. In this case, if we only have one attribute that we're looking at, horsepower, then the utility function might be 3 times the horsepower. Pretty straightforward. But then if we have a user whose utility function is modeled by B, this is a convex function because they're what's known as a risk-loving individual. In cases where they have the option, they'll take on more risk, even if it doesn't necessarily benefit them as much as it should. What I mean, I don't want to go too detailed into that just because it's not particularly important, but that's what we were looking at with the different preferences they could have. The other possibility is line C, which represents a function that exhibits diminishing marginal returns. So I don't know who's taken an economics class here, but the basic idea is that perhaps they want more horsepower up to a point, but at some point, if you can already tow a boat, then you don't care about having that much more horsepower. And so, because of that, then their function will eventually level off in this manner. And so, what we attempted to do is we attempted to see, okay, we know that the maximum regret ratio for linear utility functions can be pretty small in practice. The question is, can it be small in practice for these other guys? And thankfully, we answered that affirmatively. If we hadn't, we feel bad about our research. But we managed to do that. These are the kinds of utility functions that we ended up seeing and testing for later on. And so we managed to run a bunch of simulations on real and synthetic data to get an idea of how we did, and we also proposed a couple new algorithms for figuring out this problem. And if you're interested, I encourage you to check out our poster that Taylor will be presenting over there. It's poster number 1. Thanks very much, and I'll take questions.
Okay, thank you, Will. Time for questions. Yeah, Sean?
So you don't know their P star going in, right?
Yes, that's correct.
So what you're trying to do is minimize the regret ratio over the worst case P star.
Essentially, yes.
Well, it's really any possible P star they could have, not necessarily, you don't find what the worst case is. It's any possible P star.
Right. But since it could be such a, so you got to pick points all over the place because you never know. Okay.
Yeah.
Okay, other questions? Yeah.
What data were you actually working with? Was it, I'm guessing it wasn't about cars, but maybe it
Yeah,
was.
it wasn't, unfortunately. We did have a couple of data sets that were provided to us that they approximate real data sets. They use a lot of real data. They were never used in a database. But what we mostly use is for the people actually I believe I have, yes, for zone E and the selected references, the third one over here. They created a data set generator. So they had a lot of different data sets that were like the one with the cars, but we were able to customize a lot of different things, like the number of points, the number of different attributes that we're looking over, and then figure out how we did versus those.
Any other questions? Okay, thank you, Will.